Hello everyone, and thanks for joining us on today's webinar on optimizing the performance of next generation memory or DDR5. My name is Emil. I am an RF applications engineer at Emworks. So before we start, I would like to give you a short summary about what we are going to discuss today. So first, we'll talk briefly about DDR5 technologies, then we'll look at some of the design challenges. Following that, we'll have a case study of the connector. At the end, we'll have a live demo. So in case if you have any question, I'll be happy to answer them at the end of the presentation. So before we begin, I would like to give you a short overview about Emworks company. Emworks is a leading provider of electromagnetic simulation software for electrical and electronic designs from DC to millimeter wave frequencies. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a very wide range of applications, ranging from electric motors, generators, transformers, and power electronics, to antennas and various wireless circuits and components. HFWorks, which is the software that we are going to use today for this simulation. So HFWorks is an antenna and electromagnetic simulation software for RF, microwave, millimeter wave, and high-speed digital circuits. It uses state-of-the-art finite element solvers and machine technologies to compute fields as well as antennas and circuit parameters. It also comes with an integrated electrothermal solver. Alright, so now let's talk about DDR5 technology. DDR5 or double data rate 5 is type of synchronous dynamic random access memory technology used in computer systems to provide faster data transfer rates and improved performance compared to previous generations. It offers several advancements in terms of speed, capacity, and efficiency. DDR5 is used in many areas such as personal computers, servers, and data centers. Servers and data centers benefit from DDR5 higher data transfer rates and increased capacity, which can lead to improved virtualization, faster data processing, and better handling of large workloads. High-performance computing is another area where DDR5 is utilized. DDR5 is used in high-performance computing environments such as scientific research, simulations, and complex data analysis, where large amounts of memory and fast data access are crucial. Gaming systems and networking equipment are other areas where DDR5 is being used. DDR5 can be found in networking devices, routers, switches, and other communication equipment where high-speed data processing and low latency are important. Now let's look at the key differences between DDR4 and DDR5 technologies. DDR4 and DDR5 are different generations of RAM using computers and other electronic devices. Here are some of the main differences between DDR4 and DDR5. So first, let's talk about speed and bandwidth. DDR5 offers higher data transfer rates and increased bandwidth compared to DDR4. This means that DDR5 memory modules can deliver data to and from the CPU and other components at a faster rate, potentially leading to improved system performance. Data rate is another important parameter to consider. DDR4 typically operated at data rates ranging from around 2,133 MT per second up to 3,200 MT per second. MT per second here stands for million transfers per second. DDR5, on the other hand, starts at higher data rates and can go up to 4,800 MT per second and beyond. And this allows for faster communication between the memory and other system components. So let's look at the voltage. DDR5 memory operates at lower voltage compared to DDR4, which can help reduce power consumption and heat generation. This can contribute to more efficient and cooler operation of the system. Last but not least, density and capacity. DDR5 memory has the potential to support higher memory densities and capacities compared to DDR4. This means that the system using DDR5 RAM can potentially have more memory installed, which can be beneficial for memory-intensive tasks and applications. Alright, so far we have talked briefly about DDR5 technology and some of its main advantages as compared to the previous generation. Now, let's look at some of the design challenges of DDR5. So first, let's start with signal integrity and loss. As data rates increase, the effect of signal loss due to trace impedance mismatch, dielectric losses, and skin effect become more pronounced. Maintaining controlled impedance traces and minimizing losses become crucial to prevent signal degradation and ensuring reliable communication between the memory modules and the controller. Crosstalk and noise are other important parameters to consider. Higher frequencies and tighter routing on the PCB can lead to increased crosstalk between nearby traces. Crosstalk can result in signal interference and data errors. Effective design practices such as proper spacing between traces and differential signaling techniques are essential to mitigate crosstalk. Last but not least, thermal considerations. Higher data rates can lead to increased power consumption and heat generation in DDR5 memory modules. Managing thermal dissipation is crucial to prevent overheating and maintain stable operation. Thermal design consideration may include heat sinks, thermal vias, and appropriate airflow. Alright, so now let's look at the case study of DDR5 connector. So on right, we can see an image of DDR5 connector. The boards are made of FFR material, which has permittivity of 4.4 and loss tangent of 0.02. The blue part, which corresponds to the housing, it has permittivity 3.9 and loss tangent of 0.004. The brown lines correspond to the traces of the pins. The connector is simulated from 0.5 GHz to 20 GHz. Alright, so let's look at some of the simulation results. So first, let's start with the return loss. So on right, we can see the electric field animation at frequency of 10.25 GHz. So you can clearly see power flow through the structure. Looking at the graph on the left, we can see there is a good return loss for the connector from 0.5 to almost 11 gigahertz. So at this frequency range, so the return loss is less than minus 10 dB. So now let's look at the insertion loss. So as we said before, interference, studying the interference is an important parameter, especially for DDR5, as this helps us to increase the crosstalk between the traces and the pins. And of course, this eventually prevent data errors. So looking at the insertion loss on the left, so we can see from frequency 0.5 up to 15 gigahertz, there is a good isolation between the traces of the connectors. So at this frequency range, the insertion loss is less than minus 20 dB, and this means that there is good isolation between the traces. So looking at the E field on the right, so basically for this, only one port is excited, which is port 1, and the rest of the ports are inactive or not excited. So as we can see, there is a minimum interference, so there is low interference between port 1 and the nearby ports. And this is basically the same conclusion we draw looking at the insertion loss plot on the left. Alright, so let's look at the temperature. As we mentioned before, temperature considerations is important, especially at high data rate. Studying the temperature distribution help us to prevent overheating and maintaining stable operation of the system. So looking at the temperature distribution of our structure at frequency of 10.25 gigahertz, we can see that the maximum temperature is 60 Celsius, and this is within the recommended safety standards. On the left, we can see an impedance profile as we go from port 1 to port 2. So basically, we want to see how the impedance is changing as we go from port 1 to port 2. So as we can see here, there is good impedance matching, and this helps us to prevent signal degradation and eventually maintain stable communication between the memory modules and the controller. Alright, so here comes the end of the presentation. Now we'll have a live demo where we'll show you how to simulate such structures using HFWorks. Hello again in this live demo. So in this demo, we'll show you how to simulate a DDR5 connector using HFWorks. As you can see, HFWorks is fully embedded in SolidWorks. So basically, you don't need to import any geometry. Once you finish creating your geometry inside SolidWorks, you can just go ahead and start your EM simulation using HFWorks. So just simply a tab. In HFWorks, we have 4 types of study. We have antennas, S parameter, TDR, and resonance. But today we'll focus on S parameter and TDR. For almost each type of study, we have 3 main steps. First, we need to specify the study properties, apply material, and then assign boundary conditions. So first, let's start with the study settings. So for the study properties, you can specify the level of accuracy, whether it's normal or high accuracy. If you are interested in seeing the 3D electric and magnetic field, you can click on Save 3D Field Data. Next, we need to specify the operating frequency range. So for the sweep, we have discrete sweep, we have fast sweep, we have single point. If you have frequency points in a file, you can also import them. So for this example, we have the start frequency which is 0.5 gigahertz and end frequency which is 20 gigahertz with 31 frequency points. We have 2 types of mesh. We have manual mesh and adaptive. If you are an experienced user and you know what to apply mesh control in the structure, you can use manual mesh. Otherwise, you can click on adaptive and the software will try to find appropriate mesh for your structure. If you are interested in studying, for example, the temperature distribution in your structure, you can click on thermal coupling. We'll talk about this later. So now let's look how to apply material. In HFWorks, we have our material library, which consists of a large number of materials with predefined properties. So for example, if we go under substrate and we choose, for example, Rogers, let's say we choose this material. So you can see this material comes with predefined properties. You can also create your material library. Also, you can import your material library if you have one. So to apply material, you simply right click, said apply material. You can choose the material from our material library. For example, let's say from this one, or you can import it from your material library. To edit the material properties, you simply right click and set edit material, and then you can edit the property you are interested in. So back to our model. So we have the substrate which is made of FR4. We have another FR4 substrate on the top. So this is the housing, and we have also the signal pin. Also we have the the radiation boundary or the air which is surrounding the structure. So now let's look at the boundary conditions. In HFWorks we have different boundary conditions. We have, for example, port, lumped element, PEC, PMC, PEC symmetry, PMC symmetry, radiation boundary or the absorbing boundary. So for this example, as you can see, we have 28 ports. All of them are lumped port. So if you see, for example, port 1, this is right here, and this is the ground. Same thing for port 3. So basically we have 7 ports from this side, another 7 from this side, and 7 on the top right here, and another 7 at the bottom right here. So let's say also you can apply mesh control. So for example, if you choose manual mesh, then you can apply mesh control on bodies or faces or even edges. You can also specify the element size. For example, if I'm interested, for example, applying mesh control on this face, I can click this, or in this edge, and so on. Alright, so let's look at some of the results. In HFWorks we have what we call the results table, and this table basically gives us a summary of these circuit parameters such as generalized S matrix, renormalized S matrix, impedance matrix, admittance matrix, port results, VSWR. We can print results versus current frequency or all frequencies. Also we can export results to different formats such as text file, CIT, SPC or touchstone. So let's say if you want to plot, for example, the return loss, you simply right click, set 2D plot, and then let's choose, for example, S11, and then for example S22, and then set add. So here we go. So you can see S11 and S22 versus frequency. Also we have a listing, so we can see the frequency. You can see the S parameter versus frequency in tabular format. Also, for example, if you're interested in, for example, the insertion loss, so basically if you want to find the isolation between the ports, let's say if I want to find, let's say, S1 3 and S3, for example, 5, right here. So you can clearly see the coupling between the ports. So also we can see the 3D E field. Can even animate it. If you right click, we said animate, say versus phase. So now it's loading frames. So now you can clearly see the animation of the electric field. Similarly for the magnetic field, you can again right click and set animate. Alright, so let's look how we can find the temperature distribution for our structure. So again, this is our design. So under study properties, so basically we kept the same study settings, but this time we only clicked on the thermal coupling. So we kept the same material boundary conditions. So for thermal coupling is part of the post-processing. So basically we keep the same mesh, same boundary condition, and same material. So for this, if you right click, you said new coupling, so you have steady state, we have also the transient thermal. So for this, you can specify for which frequency do you want to find the temperature, and also you can specify the input power, and also what ports you want them excited. So for this we have already coupling case. So for this, so we're interested in 125 gigahertz. So I want all the ports excited. So it's 0.1 watt. So next thing we need to specify the thermal input. So we have different thermal inputs. We have temperature, convection, heat flux, volume heat, and radiation. So for this example, we need to show the air. So this is our convection boundary, so which is the air. So for convection we can specify the convection coefficient and as well as the ambient temperature. So once you define all of these, so you come right here and then simply right click and send run. So now let's look at the temperature of the structure at 125 gigahertz. So for this I need to hide the air to better see the temperature distribution. Yeah, so for the input power of 0.1 watt, so you can see the maximum temperature distribution, which is 60.3 Celsius. Alright, so let's look how to set up a TDR study. So TDR study is an important study which helps us to find discontinuities in the structure, and this is important especially for signal integrity. So for TDR study, for properties, so again we can specify the level of accuracy, whether it's normal or high accuracy. So for time sweep, so we can specify the race time as well as the number of time steps, in addition to the number of time steps. So we kept again the same materials, boundary conditions. And now, so for this, first we need to create configuration. So say right click, new configuration, and then we said let's say loaded. So and then we can specify which port we want it excited. Let's say for this we want port 1, and then so for the other ports is 2, 3, and 4. We want them loaded with the resistor with 50 ohm. You can also change the load type. So you can, for example, leave it open or shorted, etc. And then after this, so then you can right click to the plot. So for this is configuration 1. So right click. So now you can clearly see the impedance profile versus time for port 1, when the other 3 ports are loaded with a resistor of 50 ohms. Here comes the end of the live demo. So in conclusion, you have gained an understanding of the factors that an electromagnetic engineer must take into account while designing DDR5 connectors. We have illustrated you how HFWorks can assist in addressing crosstalk, preventing system overheating, and ensuring reliable communication between the memory modules and the controller. With that, I would like to thank you, and now the floor is open for questions. Thank you.